welcome back to my office hours. In this video, we'll discuss the differences between centroid and center of pressure, how to calculate the hydrostatic force, and how to locate the center of pressure. We will also solve one example problem together. First, centroid versus center of pressure. According to the hydrostatic equation, the magnitude of hydrostatic pressure P increases as the elevation Z in the fluid decreases. When hydrostatic conditions prevail, any panel that is not horizontal is subjected to a hydrostatic pressure distribution. A pressure force acts at a point called the center of pressure, which is calculated so that the torque due to the pressure force is exactly the same as the torque due to the pressure distribution. In other words, if you want to replace the pressure distribution with a statically equivalent force that acts at a point, the correct point is the center of pressure. Meanwhile, the centroid of an area can be thought of as the balance point of an area. In general, the equations for finding the centroid are integrals. For common shapes, the equations have been solved, and engineers look up the value. Let's pause a few seconds on this page to review these equations developed for various common shapes. The hydrostatic force on a panel of arbitrary shape such as rectangular, round, or elliptical is given by the product of the panel area A and the pressure at the elevation of the centroid G, location of the center of pressure. The torque due to the resultant force Fp must balance the torque due to each differential force. As shown here, Yc is the slant distance from the center of pressure to the surface of the liquid. The label slant denotes that the distance is measured in the plane that runs through the panel. By the parallel axis theorem, the following equation can be derived for the slant distance from the center of pressure to the surface of the liquid. The area moment of inertia Ig is taken about a horizontal axis that passes through the centroid of area. Formulas for Ig can be found in the literature. Here, I have listed some examples. The slant distance Yg measures the length from the surface of the liquid to the centroid of the panel along an axis that is aligned with the slant of the panel. This equation shows that the center of pressure will be situated below the centroid. The distance between the center of pressure and the centroid depends on the depth of submersion, which is characterized by Yg, and on the panel geometry, which is characterized by Ig over A. With this background knowledge, let's work on one example. Problem statement. An elliptical gate covers the end of a pipe 4 meters in diameter. If the gate is hinged at the top, what normal force F is required to open the gate when water is 8 meters deep above the top of the pipe and the pipe is open to the atmosphere on the other side? Neglect the weight of the gate, and neglect friction between the bottom on the gate and the pipe wall. Assume water temperature is 10 degrees Celsius. To solve this problem, we will need to do the following. 1. Calculate the resultant hydrostatic force using the pressure at the depth of the centroid. 2. Find the location of the center of pressure using the slant distances Yc and Yg. 3. Draw a free body diagram of the gate. 4. Apply moment equilibrium about the hinge. Great, let's begin the work. The area of elliptical panel is calculated using the area formula. We have A equals to 2.5 meters and B equals to 2 meters, resulting in a panel area of 15.71 square meters. The depth of the centroid is 10 meters, which is calculated using 8 meters plus half of the pipe diameter 2 meters. The specific weight of water at 10 degrees Celsius is 9,810 Newton per cubic meter. Therefore, the resultant hydrostatic force is calculated using the hydrostatic pressure times area, and we have 1.54 million Newton. Now let's work on step 2, finding the center of pressure. If we extend the water surface line and the panel line, we will be able to find that the slant distance from the water surface to the centroid Yg is 12.5 meters, calculated using 10 meters plus half of the gate height 2.5 meters. The area A has been calculated previously. It is 15.71 square meters. The area moment of inertia Ig of an elliptical panel can be calculated using the corresponding formula. Here we have A equals to 2.5 meters, and B equals to 2 meters. The result is Ig equals to 24.54. Finally, by substituting these values into the equation, we can find that the distance between the center of pressure and the centroid is 0.125 meter. Step 3. As we draw the free body diagram of the gate, it is clear to see that there are only two forces on the gate. One is the hydrostatic force, and the other is the normal force F required to open the gate. The length of the moment arm for the hydrostatic force is 2.625 meters, which is calculated using the distance from the centroid to the hinge 2.5 meters plus the distance between the centroid and center of pressure. The length of the moment arm for the normal force F is 5 meters, namely the fully height of the gate. Step 4. The minimum requirement to open the gate is when the moment due to the normal force F balances with the moment due to the hydrostatic force. Following this idea, we calculate the minimum value for the normal force F should be 809 kN. Thanks for watching. Leave a comment if you have any questions.